least hopefully more rain, gradual rain, headed our way. So this is obviously an Institute for Energy Efficiency seminar. Next week there'll be another one. Manoush Alazenda, I always have trouble with her name, fairly new professor of electrical engineering. We'll talk about electricity demand management for networked infrastructure systems. So again, as we get more and more solar power and wind and fluctuations, she's studying how to manage that in terms of a robust grid. So today we're happy to have Jordan Sager speaking. So he's in facilities, and he's the one responsible for all of the solar panels going on all of our roofs. We'll hear a lot more of that on all of our parking structures. You can take credit for it. It's a good, this audience, it's a good thing.
I don't know. Does anyone park over at lot 10? I might not want to take credit for that.
I think it's great. So Jordan, the floor is yours.
Thank you. Get my slides going here. Rachel, can you help me out for just a sec? So thanks for the introduction, John. As John mentioned, my name is Jordan Sager. I work in facilities management for the campus, and I've been here on campus for about 9 years. I'm a Bren alum, so proud gaucho, and I've been working on energy efficiency and energy management, utility cost management projects for the campus for a number of years now, and it's been a pleasure to kind of gain some exposure to what the IEE is doing and build our collaboration there. I'll talk about a couple things that we've worked on together. My talk, I want to start out and just kind of give an overview of the campus and our energy use profile and sort of our regional context here. Talk about some problems, or I should say some challenges that we're facing as a campus, but also kind of solutions that we're working on using technology to kind of meet what we see as kind of the future imperatives in the energy realm. Some of that technology developed right here at UCSB in the College of Engineering, so some great things to touch on there. I'll talk about our campus electric utility infrastructure, the on-site energy resources to date that we've built, and an exciting kind of effort that we're getting underway for building HVAC or mechanical systems analytics and how we're making use of those for energy efficiency in our existing buildings. So most of you know kind of the campus layout. Generally, we've got main campus, Stork campus, and then everything out west, right? So we've actually got about 1,100 acres of space. Main campus is only about 400 acres of that. So less than half of the space is what most of us know as UCSB, the main campus here. But well over 95% of the energy use and the resources consumed are here at the main campus. So I was digging around and I found our 1953 master plan for growth. This is the main campus here. So we have definitely outgrown those ambitions, and today we've got about 8.5 million square feet of space. That includes our housing, labs, offices, dining commons. That's everything. This is our growth since 1990. As a campus. So we were at about 4 million square feet, 4 million and change in 1990. And over the past almost 30 years, you can see we've nearly doubled in square footage. We're at about 8.5 million square feet now. And between the times of about the mid-2000s to 2008 or so was a period of rapid build-out. Those of you who were here saw a number of lab buildings go up. We had dining commons built. We had some housing as well. But for the most part, energy-intensive space is what we were adding at that time. Here's an example from our beloved engineering science building, the nanofabrication facility, definitely energy-intensive space. Data center is another example in our effort to kind of consolidate our data management and add security and robustness to our system. We started to build out the North Hall data center. We've added a lot of housing in the past 5 years, so we've got 10,000 students now housed and fed on campus, which is significant. All of these things adding to our energy bills, but also adding to kind of our stature as a campus, right? So last year, number 37 among national universities, number 8 top public schools. So we're climbing in the rankings, which is fantastic. We've got the research space and accommodations to facilitate the high-end research that we're doing, and we've seen numerous Nobel Prize winners and high-dollar grants come through for both the College of Engineering and Letters and Science. So we are on an excellent trajectory academically. Energy use-wise, this is the same time period. This is 1990 to 2017, and this is in terms of BTUs. So we've got natural gas in yellow and electricity there in blue. And this is absolute usage presented in trillions of BTUs. So you can see over that time period, we've been up, we've been down. We started our kind of our current energy efficiency campaign, and when I say we, the University of California and the state investor-owned utilities started the statewide energy partnership for higher education. So that's the UCs and the CSUs, as well as the community colleges in the state, and that provides for pretty good incentives for energy conservation, as well as financing for projects. So that started in its current form in 2009. So you can see we really started to hit the energy efficiency hard in 2009. We did have 3 very warm winters in a row there in 13, 14, and 15, and that helped our numbers quite a bit as well. But the long-term trend, I think, kind of tells the more important story. This is our grid energy use intensity. So this is both commodities that we bring onto campus and consume, electricity and natural gas in kBTU per square foot per year. So back in 1990, we were on average just about 100 kBTU per square foot. We peaked at about 120. For the past few years, we've been around 65,000 BTUs per square foot per year. And that's really the metric that we look at from the very highest level. That's how we do our energy benchmarking for whole buildings or building spaces. It's that kBTU per square foot per year metric. It's a rough and dirty way to kind of assess efficiency of the campus or a building, but it's a good place to start. Monthly power use doesn't vary much. Seasonally, we see a pretty consistent load. Natural gas, however, obviously varies. The biggest use of natural gas on campus is space heating, comfort heating, so that does vary seasonally pretty significantly. In terms of expenditures, electricity by far the greatest expenditure when it comes to what we actually pay out for utilities. $7.25 million in 2017, actually followed by potable water. For the first time, water overtook natural gas as a utility expense. We spent about $1.8, $1.9 million on potable water last year and only $1.25 million on gas. Water's going up. Gas has been at historical lows for a number of years, as many of you know, but that's a pretty interesting trend from our perspective. This is our on-campus solar purchases. So the power purchase agreements that we've signed onto, you see all these solar sites going up. We purchase power from a third party who owns, operates, maintains those systems. So that's what you see there. And then we've got reclaimed water here, a little sliver for landscaping, and sewer there. So let's kind of talk about the regional context for a second. We're going live here, so bear with me. This is the Southern California Edison publicly available GIS data for their transmission and subtransmission circuits. So the blue outline that you see is SoCal Edison's service territory, right? That's the entire territory served by SCE as a utility in Southern California. To the south, they're served by San Diego Gas and Electric, and to the north, primarily Pacific Gas and Electric, with some carve-outs in LA for municipal utility districts, and that's the case all over the state. So here we are, right? You can kind of clearly see we're we're out there at the end of the service territory. I'm going to drop the transmission circuits on here, take off the low voltage stuff, and kind of zoom in and show you how we get our power. So the purple lines are the 220,000 volt circuits that run all across the state. So that's transmission level power. The orange lines are sub-transmission level power. That's 66,000 volts, typically 69,000 sometimes. But our 220,000 volt circuit, here we are down here. Here's the Goleta substation. This is where we're fed from. This 220 kV circuit runs all the way down to this substation. This is the Santa Clara substation. So that's where our 220 service originates. It's also where our 66 service originates, and you can see there are 3 orange circuits that come up from Ventura and serve Carpinteria, Santa Barbara, the areas between Goleta and Santa Barbara, and then eventually meet up at the Goleta substation at the same spot that the 220 kV comes in. So we've got 3 66 kV circuits, 2 220 kV co-located circuits. And that's what all this fuss about resiliency in our area has been about, is really this 220 system. Because the 66 kV system, it's a backup, basically. It's what we call normally open. They're tie lines. So we wouldn't typically be served all the way from Ventura by that system. We would be served by the 220 and then kind of partially served by the 66 here. The 66 would serve the other part of our territory from the other direction. The reason for that is, on a peak day, there's too much load here for this 66 kV circuit to carry. So that is kind of the biggest problem that we're facing in terms of power reliability is, you've got the Whittier fire territory here, the Thomas fire territory here. The power lines are robust. They're not necessarily susceptible. If a fire passes underneath them, we can still be up, which is what happened during the Thomas fire. We had interruptions, but the reason that we didn't switch over completely to the 66 was because one of those 3 lines was down for maintenance. So we couldn't do that. We had to ride it out on the 220, and that's why we saw those kind of momentary interruptions, those blips, right? Those really kind of problematic periodic interruptions where we're bouncing on and off are not good for our systems at all. So that's a little bit of context. We're going to come back to this in a bit. Zooming into campus, I just want to show you, here's our dedicated 66 kV circuit. You can see there's us. Circuit runs up to the Goleta substation. So we've got our own substation on campus. And what we do there is we take 66,000 volts from the utility. We've got a 66 to 12 kV transformer system, actually 2 of them in parallel, and that's how we serve the campus. This is our campus switchgear. So 12,000 volts. There's a lot of smarts in this system. We've got 4 loop circuits that essentially run around the entire campus. So here's our substation. We've got Research North, Research South. We've got a central academic in yellow, and then we've got a housing and auxiliary loop. So these things actually run in the same duct bank in a lot of areas, and we've grouped buildings, not necessarily geographically, but sort of by building type. So we've got a bunch of heavy science and engineering buildings on the research circuits. We've got kind of central academic state-funded buildings on that CA circuit, and then housing picks up all the housing, as you'd expect. We ran housing recently out here to Stork and El Colegio and picked up all the new housing in that area. So we're sort of reaching out with that 12 kV circuit to pick up additional loads that we own in Isla Vista. Someday this will probably run all the way to Devereaux, and will probably serve any development that happens out there as well. We don't have any on-site generation. This is a picture of UCLA's cogen facility. So this is a 53 megawatt gas turbine that generates power for UCLA and also generates steam for the campus. So they've got an old steam distribution system, and that is how they do most of their heating. 6 out of 10 of the UC campuses have some form of on-campus generation, power generation, and if anyone remembers 2003, the big fires in San Diego, a lot of San Diego was without power. UCSD at that time had the ability to island off the campus and generate enough power to keep the campus running and essentially keep all of their critical functions and more powered up. Not only did they do that, they powered some of these substations in the adjacent community as well, actually pushed power off campus and powered up commercial and residential properties because they could. They had the capacity. UC Irvine recently ran a test. They're able to island their campus and disconnect completely from the grid. We're not quite there yet. What we do have is sort of a growing network of distributed solar PV sites. So up until 2016, we had about a half a megawatt of PV, about 500 kilowatts of photovoltaics on campus. In the year 2017, we increased that by an order of magnitude. We've got about 5.5 megawatts on campus now of capacity, and that was primarily the parking garages that you saw, a couple of rooftop sites. It was a large lot out kind of on the periphery of campus near Harder Stadium, and that project was all done under a power purchase agreement, as I mentioned. It was sort of a financing mechanism whereby we lease our sites to a solar developer for 20 years. They build these systems for us more or less to our specifications, and then we agree to buy the power from those sites for 20 years at a pre-negotiated rate. So all of that is kind of worked out in the business arrangement, and those all just came online in 2017. So I've got some photos of construction for you because that's kind of fun. This is the Harder Stadium parking lot. This is the biggest site by far. It's about 2 megawatts. Surface parking. Now everybody's got shaded parking, so that was kind of a co-benefit of that site. There's a view from above. There's an adjacent parking structure that serves some student housing. This is the Mesa structure. I like this picture because this is the biggest crane I've ever seen. It was a 340-foot extension boom crane, and the reason we required them to use something so large was we didn't allow them to shut down Ocean Road. So they wanted to shut down the road and lift from both sides. We said, this is all you get. Road has to stay open. Basically do what you can. This was actually an example of a big difference between working with a general contractor and kind of our typical design, bid, build approach. It's how we build all our buildings. A lot of times when we force them to do something that might be extra or wasn't in their contract, that's how they make their money. With these guys, with this solar company, there was a lot of give and take. We allowed them to do some things that made their job easier, and we forced them to do some things that were a little bit of a workaround. We kept on falling back on sort of one provision in our contract that said they could not interrupt campus operations for anything. So that's open to interpretation, and anytime something big came up, we said that's a big impact to our operations, you've got to do it that way. So that worked out just fine. Anybody park in Lot 10? Probably recognize this. So sorry for the disruption last summer. We actually saved this one for the summer to make it easier on everybody. But we did understand that shutting down the top level of a parking structure around here, especially this one, can cause some headaches. Again, I do really like this picture. This was a day or two after this system was built and came online, was being commissioned, and you can just see the guys up there on the lift cleaning off the panels. That's another nice thing about this power purchase agreement arrangement is we do not touch this equipment. The developer and the owner has every incentive to keep these systems running optimally, or else we're not going to buy the power. So they don't make money if they don't sell power. They've been up here every 6 months cleaning these systems. Whenever an inverter trips off, they're here, they're troubleshooting. I can tell you, work in facilities, this would not be our top priority. If an inverter failed or if panels were dirty, you guys know that. That's obvious. So that's what we've got. We actually do have a contract with the same company to add another about a megawatt of rooftop sites. Smaller sites, it's kind of our tier 2 list. We hit the big stuff with this first round, and this is sort of a, well, we have the contracting mechanism in place. SunPower is a known commodity. They know the campus. They're on site. So we're going to do another megawatt. So that should be moving forward this spring and summer. So what's this doing to our electrical load? It's interesting. This is a week of power demand data for the 66 kV substation. So we have 1 meter that serves the whole campus at that substation. And this is Saturday through Friday. So it's 7 days. You can see the weekend. We're anywhere from 8 megawatts plus to 11 megawatts. And then during the week, we peak at about 15. And it's pretty typical, pretty predictable load. I chose this week to look at because it's really the first week that classes are back in session, typically pretty hot. The campus is kind of at its highest use levels, its highest demand levels. So 2016, that's what our load looked like. 2017, after we put all the solar in, this is now what we're seeing at our substation meter. So you can see the effect on the weekends, particularly our base load now is no longer at night, it's during the middle of the day on the weekends when there aren't a lot of people on campus, when building ventilation systems are shut off. We see this big dip now when our solar is generating. During the weekdays, we also cut out a big portion of midday use, but what we're left with now and kind of what we're grappling with is this big spike at the end of the day. This is great. This delta saves us a lot of money. Not only are we not paying for the kilowatt hours, but we're not paying for the demand that we set, right? We're taking our peak down from 15 megawatts to about 13 megawatts, which saves us hundreds of thousands of dollars in the summer on each of our monthly bills. This is still a problem though, right? That's room for additional savings. Does anyone know the name of that phenomenon? It's been pretty popular. David knows. Yeah, that's right. It's the Cal-ISO duck curve. And this was predicted pretty early on, and it is absolutely manifesting not only at a regional level, but at customer meters like ours. And it's compounded over the state, particularly in the spring months when it's cool and there's a lot of sun. We've seen utility scale solar systems have to curtail their power because they're over-generating during the middle of the day. We've also seen this sort of wreak havoc with utility kind of rate modeling assumptions, right? The traditional kind of rate model reflected the fact that most of your load was in the early afternoon, mid-afternoon times when it was hot, when people were using the most power, and that's when the most expensive power was to produce, and rates were sort of modeled as such, right? So traditionally, this is sort of a 24-hour period. I got this from Edison's website, so if it's ugly, it's their fault. 6 to 9 on weekdays, and 10 to, well, actually 10 p.m. to 6 a.m. all the time, so off-peak power. So let's say that's 5 cents per kilowatt hour, 5 pennies. In the summer, we see mid-peak rates from 9 a.m. to 12, and then again from 6 p.m. to 10 o'clock. And then we see our on-peak rates from noon to 6. That's the kind of peak pricing, traditional structure, and we've been paying on that rate for years. So let's call this 5, 10 cents, and on-peak would be about 15 cents. In the winter, things are a little bit different. We just don't have that on-peak rate. So we're mid-peak on the weekdays all day long. In 2019, this is coming. Utilities all across the state are trying to deal with this duck curve, right? And they're trying to essentially make their rates reflect the fact that now power is the most expensive to produce in the late afternoon, early evening when we see those ramps, right? When we've got to ramp up all that generation all at once. So our peak pricing is going to be shifting back from noon to 6 to 4 to 10 will be our peak pricing. And guess what? Our peak is 8 p.m. So it's right in that time frame. So this does do a really good job capturing kind of the new statewide load profile, given all the solar that's come online.
Jordan, quick question.
Please.
Can you go back 2 slides? Yeah. You said, this has cut our costs because we don't have to pay for that big peak in the middle of the day. But
Yeah.
we do have to pay the solar provider.
Yeah, that's an important distinction. So I guess in a nutshell, the avoided cost with solar for that power, so what we would be paying SoCal Edison, is about 14.9 cents. The rate for the the electricity that we're buying from SunPower is 11.75. So there's a 3-penny delta. We get about 10 million kilowatt hours a year from the solar system. So we save about 300,000 year one. Solar rate stays the same for 20 years, by the way. I would be surprised if Edison's rates did that. So there's our duck curve, right? This is a typical day in the spring. We've got our 2016 load and our 2017 load. So what now? What do we do about this? We are working on efforts now to kind of go after some significantly sized battery storage systems. So we knew when we put the solar in, we started to see what this was doing to our load profile, started to model kind of what our savings could be if we were able to move those peaks around, say charge during the midday, charge during the night, and discharge in that afternoon, evening time frame. So we ran a pretty extensive analysis in early 2017 to look at what the optimally sized and configured battery storage system for the campus would be to provide sort of the most marginal economic benefit. And what this shows is sort of different sizes in megawatts there, and then durations in hours. So megawatt hours is kind of the important number. So a 4 megawatt 2-hour battery would give you 8 megawatt hours. And I picked this one because we decided this was pretty much the sweet spot. These blue bars represent total bill savings. So obviously a small battery gets you a small bill savings, but your simple payback is going to be quite a bit better, that's this orange line, than a very large battery, which would get you big savings, but you're sort of hitting diminishing marginal returns at that point. So we decided that this 4 megawatt, 8 megawatt hour battery was the one that we wanted to go for. Looking at that a little bit more closely, this is a 4 megawatt battery of different durations. So this is the one that we're looking at right here, 4 megawatts for 2 hours. Simple payback period, about 12 years, were we just to go and purchase this and install it and run it. That's what we could get by managing that demand a little bit better. I should say optimizing that demand would get us that 12-year payback. Best case scenario. So a good opportunity came up in the summer. The California Energy Commission issued a number of grant funding opportunities in August. One of them was GFO 17302. The name of this opportunity was Demonstrating Business Case for Advanced Microgrids in Support of California's Energy and Greenhouse Gas Emissions Policies. This was the largest CEC opportunity that had ever been offered. $44 million total in 3 groups, and we decided that this was a really good one to go for, and it was really good timing for us. So we had a team from the Institute here, the Institute for Energy Efficiency, Electrical and Computer Engineering Department. In fact, Manoush, who's going to be presenting next week, was one of the faculty members who collaborated on this and would essentially be doing a lot of the research to support the project. And then, of course, facilities management. This had a lot of really interesting components: energy storage, advanced EV charging, utility demand response, this sort of advanced integration platform to bring all these resources under sort of the same command system, and also the ability to island a part of the campus, not the whole thing, but we were going to segment off a piece of that 12 kV system that included the police department, fire department, emergency operations center, communication services, our evacuation shelters. with some high voltage switching. That segment included about 3 megawatts of solar, including the big one out at lot 38. Put a battery in, and we could run that segment of the campus indefinitely. So it would be kind of thing where if we had a landslide that took out the 220 lines and the 66 lines, we could run that portion and keep that section of the campus up. So there was a pretty strong resiliency and emergency response component. Also significant value generated during normal operations, right? Demand management and a lot of opportunities that the utilities are starting to introduce to provide demand response. So if they say, hey, we're 2 megawatts short, can you provide 2 megawatts for 2 hours? We'll pay you X amount. Those opportunities are significant. And of course, rich research opportunities in DER integration, DER being distributed energy resource. Unfortunately, we learned about a week ago we did not get the award. It was a very competitive solicitation. There were 30 respondents. We were a finalist. We were about number 5. I was just talking to John before this. We're going to go for it again. We had a fantastic team, and we put together a really strong proposal. So we're going to kind of learn from that and move forward with the next CEC opportunity when we can. Another opportunity presented itself actually yesterday. This was introduced. Everybody kind of knew it was coming. Again, this is Edison's response to that reliability question. There was an RFP that was put out in early 2017 and then pulled back for distributed energy resources, specifically in the Goleta and Santa Barbara areas. Primarily storage, also solar and storage hybrid. The reason for the kind of issuing and then pulling back that RFP last year is a bit unclear, but they just reissued this again yesterday. And this opportunity targets specifically our 66 kV system, right? So this is sort of a conceptual diagram of what I showed you from Edison's GIS layer with the Santa Clara sub, the 220, and then the tie lines here. So they're looking for 55 megawatts in our area, which is significant. It's going to be tough to find siting for 55 megawatts, I think, around here. That's in front of the meter and behind the meter. So for us, that would be a behind the meter project, something that we host, something that we build on campus and use it on a day-to-day basis. And then when there's an emergency, we say, okay, Edison, we'll give you 4 hours twice a year. That's what you get. Then they can call anytime they need to, and they can dispatch that system to provide power to their 66 kV if we have another big fire or a landslide or an earthquake or what have you.
Where does power come from that goes to the substation in Santa Clara?
This power?
Yeah.
That's a good question. So there's the Oxnard generating station. I mean, it's essentially the generation anywhere in Southern California. Yeah.
Follow-up question to that.
Yeah.
Whatever happened to the peaker plant that was out in Goleta?
Good question.
And how big was it?
It was about 55 megawatts. 53, I think. Yeah, so Edison applied for a relicensing permit to the Public Utilities Commission last year, and what they wanted to do was retool their gas turbines and put in a bunch of battery storage. And the PUC was lobbied pretty hard by some environmental groups and community groups that said, we don't need fossil fuel generation, we can do this with renewable sources, we can do this with batteries, we want you to scrap the Elwood peaker plant. And the commission did just that. And it was just about that time that the RFP for distributed energy resources in our area got pulled back. The two are connected somehow, but I'm not in that world enough to know why or what happened. In terms of load in our what they call a load pocket in this 66 kV Goleta Santa Barbara area, our peak load is about 285 megawatts, and we're about 15 of that. So between the three 66,000 volt lines, they've got about 230 megawatts of capacity. That's how much they can deliver. So in the worst case scenario, they'd be short in the day by about 55 megawatts. So that's where that number came from. So this zero line here represents the full capacity of that secondary system. At night, of course, they've got surplus capacity. In the day, they're about 55 short. And this is straight out of an Edison presentation with their solicitation package. So we'll be paying very close attention to this to try and chase some of that funding for on-site storage. We got a little bit into the weeds here on this analysis and also sort of derived what the implied capacity payments for a storage system from Edison would have to be to make this system pencil out for us. So we know when developers are coming and talking to us what their costs are likely going to be, and we've got all of our ducks in a row, I think, for planning what's best for the campus under this offering. Same one.
My understanding is that the battery capacity goes down over time, and it was the payback period incorporated those replacement costs as well?
Yeah, it did. It did. We actually, I wish I could say we, I wish I could say we did this analysis ourselves. We didn't. We had a company called E3 up in the Bay Area run this for us, and they do a ton of this kind of work, and that was definitely a variable that was considered, as well as what the changes to rate structures are going to be. They did a whole bunch of sensitivity analysis as well. Yeah. So let's keep going. Okay, so I want to switch gears. Yeah, do you have another question?
There's the county and the cities in the county that are also going to the same
Yes.
thing. Are
Yeah.
you working together at all? Or?
We are. In fact, you've got a county rep right there behind you, and we are. We're all paying very close attention to this. We have Edison is putting on a bidders conference in 2 weeks. We've got a series of kind of community workshops that are actually being facilitated by the Community Environmental Council. That's a group that really wants to see our community take full advantage of what could be a really great opportunity for us, not just for carbon savings, but resiliency and power reliability. So we are definitely talking to one another and trying to figure out how there might be some kind of shared benefits there.
This curve is a little odd. The 1 megawatt, 4 megawatt hour is very cost effective, but the 6 megawatt hour is much higher. Why is that?
Yeah. That's a good question. I'm sure I'd say that 1 megawatt, 4 megawatt hour battery is sort of one of the smaller batteries in the mix, right? So obviously what factors in here is our payback and sort of our marginal returns for each battery size. The smaller the battery, the better the sort of per unit payback, because we're just hitting that peak. I would say that's probably the driver for that, the primary driver. But without looking at the model, I probably couldn't tell you exactly. Yeah. I think I'm going to end on that topic and open it up for additional questions if anybody has any. I want to thank David or John and the Institute for Energy Efficiency and Roger for having me here, and it's been great working with the Institute, and I hope we get a chance to collaborate in the future.
Questions? We have a microphone for the filming of this, so if you raise your hand, I'll bring the microphone to you.
This is a follow-up on your question about that peak. Several slides ago, you showed, the cost of the battery systems, and there were back farther, there were two very dramatic peaks in the cost, and I'm wondering why that was. Was that a sizing thing, or? No. What was the one where was the one that showed the battery cost per megawatt, or?
This guy here?
Yeah, well, further back, you were showing the choice of size of. Yeah, I guess that would.
I think this was the first one.
See
yeah.
You see those two very monumental peaks there
Yeah.
in certain battery
Yeah.
sizes. Any idea what, is it space or?
So that is a 4 megawatt, 32 megawatt hour battery. So actually the capacity, so it can discharge, I'm looking at this one right here, right, compared to the 4 megawatt, 20 hour battery. So this thing can discharge 4 megawatts at a time, but for a much longer period. So my guess is just the associated equipment needed for a smaller battery with a longer discharge would drive that high cost there, as opposed to something like this 20 megawatt, 40 megawatt hour battery. And keep in mind, this is the simple payback period here. So calculation between your bill savings and then the installed cost of the system, not total cost. Yeah.
Perhaps, Jordan, we will not go too much into the details of this
Yeah.
because you probably you didn't do this, but it raises a lot of interesting questions that I think, not a negative way, I think would be interesting to look into the details of this model. For
Yeah.
example, I think that, well, the campus will increase the demand as we go forward, as the enrollment increases, and how that kind of scenario is factored in, and how the rate increase kind of scenarios are factored in. Those kind of things would be very interesting
Yeah.
to look at. My question goes to the greenhouse gas emission side of
Right.
the battery storage project. And interesting aspect of the base load is that base load is not necessarily dirtier than peak load, because peak load generally is natural gas power. Generally, greenhouse gas emissions per kilowatt hour is lower than some of the base load, but it may not be the case for California. So have we done some kind of analysis? What are the implications of battery storage on greenhouse gas emission side?
Yes, that's a really good point. And our kind of our working assumption is that peak load is at least in our region almost always dirtier than base load, right? In terms of greenhouse gas emissions per kilowatt hour. The way that we report our greenhouse gas emissions to the state and to our county and our voluntary agencies does not reflect that, and it needs to. There's no time valuation for greenhouse gas emissions. If you look at the way the California Building Code, for example, treats energy use, in Title 24, if anybody works with building energy efficiency standards, that code does value the time that electricity is used and weight it such that it disincentivizes peak time usage, right? So that's a really good point in that, we're peaking now with the rest of the state. And that kind of marginal power, that peak power that we see across the grid is per unit the dirtiest power that we're going to use that day or that week even.
Yeah, that's great. Just one thing that to note on that is that, so as you said, quantifying the marginal electricity and marginal electricity emission factors is turned out to be a very complex question.
Yes.
And we are currently working with Microsoft, and there is an NGO called What Time that tried to connect the marginal demand increase or decrease on the marginal changes in the electricity grid mix and greenhouse gas emissions associated with that. So I would love to connect with you, when we are submitting the proposal again to CEC next year or later, then might be something, a component that we can add to the proposal if it is relevant.
Absolutely. The University of California is working on kind of similar lobbying effort to the National Climate Registry to kind of modernize the way that we do our reporting and actually do some time valuation of carbon emissions. So that's coming. Yeah.
Hey, Jordan, thanks for a really clear talk. You spoke a lot about electricity generation, but relatively little about efficiency, which
Yes.
is funny given the name of the series. So I'm curious, from your point of view, how much scope do you think there is to cut our electrical uses just from, I know we've done a lot already, but looking at some of the lighting around campus, for example, it seems like there's still lots of potential to work on that. So I'm curious what your big view is on that.
My opinion is our largest opportunity is, I mean, sure, capital investments in lighting and mechanical upgrades are something that's going to continue to be done as we just keep up the campus. And it's been a bit of a struggle, but we've finally got all of our electrical trades on campus really behind LEDs. We don't put in anything but LEDs. Now they're coming to me saying, hey, I've got this great idea. What do you think about this? So that's happening, and it's gained its own momentum, and we'll continue to do that. I think where the real opportunities lie are in this technology-enabled idea of building HVAC system optimization and building analytics. And I was going to kind of talk a little bit through some of this stuff, but we're using a software system called EcoRhythm that was developed. It had its start in the mechanical engineering department here, and has since kind of grown and is offering these types of solutions to mainly commercial property owners. But modern buildings have anywhere upwards of 3, 5, 10,000 monitored points, right? It's like your car. When you take your car into the mechanic, they've got to plug in to see what's going on. Buildings are like that now. The control systems that we use to essentially take feedback from building sensors and issue commands for system operation are overwhelming us with data. So new building bioengineering, for example, 10,000 monitored points. If you think anybody, we've got 3 people, right, in my office. 10,000 times how many buildings do we have? And how many are we going to build? It's just not feasible, and it's data overload. So I think the building analytics and what's kind of commonly referred to now as FDD, fault detection and diagnostics software, are where a lot of our focus is going to be. And what these software systems do is they take all of that information from your building automation system, they take all those 10,000 points and they sample them every 5 minutes, and they apply logic, and they say, okay, what in this air handling unit system, so from the fan on the roof down to the terminal unit in your office and the heating coils and your thermostat and all that stuff, is everything functioning as it could be for thermal comfort and also for energy efficiency? So we've got EcoRhythm deployed at 4 buildings now, and we're looking at expanding to more buildings on campus as we kind of get past the initial onboarding kind of workflow, right? And we sort of become more efficient at this. And this is just kind of a schematic of what I'm talking about here. So building trend data from our building automation system, architectural information, so spatial information, floor plans, fault detection, logic, web reporting that's usable and provides actionable information from all that data. And then this is kind of an interesting piece we're working on here, this idea of taking those faults that are generated by the system and integrating that with our work order dispatch. So has anyone here ever put a work order into TMA? You love it? Rob knows. Yeah, it's great, right? It never fails. It never feels like it's going into a black hole. So what happens when Rob puts his work order into TMA is he says, my office is hot, or this space is too cold. So a technician gets dispatched, and they show up and they say, okay, it's hot. Let's look around. Let's figure out what equipment serves this space, get sort of the lay of the land. And it could be a couple of trips out there before they diagnose the issue, if they do at all. Especially with HVAC. It's complicated, and it's not that our HVAC techs are not smart. They're some of the sharpest on campus, but the equipment is all hidden, the systems are complicated, it's a mechanical system, and they're getting more complicated. So these kind of, this still requires sort of a human filter to say, okay, this is a fault that's worth sending a technician out. But when we do send them out, they are going to have trend data that shows them exactly what is going on and what trends are feeding in to create this fault. So what's misbehaving? Is it a thermostat that's offline, or is it a valve that's stuck in a certain position? And essentially arms them with the information they need to only go out once and go out and fix exactly what's wrong, and maybe do it before Rob even puts in his work order. So that's what we're kind of working on, is not only kind of energy efficiency optimization, but this kind of gives us the ability now to take a building. This was the first example of the first building we ran this on. This is a before and after. This is a thermal comfort index. So you see green obviously is good. This means everything is kind of in the range that it should be, and red is a certain amount of degrees outside of the comfortable range. So we took a building that was built in 2008, applied this software, and increased thermal comfort dramatically, but also this was the number of faults that were being generated by the system, and sort of as we fixed them, faults were going down, right? We're seeing less problems. We're actually addressing things. Systems are responding in a manner that tells us that the building is in a better condition. And this is our energy use. So in blue, we've got sort of our energy use regression that we build when we start a project and say, okay, given the operations of this building over the past year, what should it be using given what the weather is doing, right? In red is what our building actually was using after we went and did the project. Schedules were out of whack. Things were put in manual that should be automatically controlled. And just digging through all of that data in our kind of native building management system interface is very cumbersome. And unless we had an army of folks to do that, it's just not going to get done. So this takes data and turns it into what I'd say is information that we can actually use. So that's where we're going, I think, for energy efficiency.
In terms of your battery calculations earlier, I presume none of that was gravity-based systems, but
This was all lithium ion. Yeah.
so how far away is a gravity-based system from being economical?
Oh, I should ask you that.
Two questions. One to follow up on this. For this building, for example, that you did as sort of a case study, were the energy efficiency improvements substantial enough to put a number on, percentage-wise? And if you were to expand that to all the buildings on campus, do you think that you could see a noticeable reduction in your base load?
Yeah, absolutely. So I would ballpark the savings that we got out of this building at about 15%, maybe a little bit less on the electricity side. But one thing we were doing at this building was starting the heating system at 3 in the morning. So building got built. A bunch of people complained it was too cold in the mornings. We sort of would take that and take those anecdotes and say, okay, we're going to be conservative. We're going to start at 3 in the morning. Through use of the software, we were able to kind of really dial in what time the heating system should be turned on to make it so it was comfortable for 80% of the people by 7 o'clock in the morning. So we cut off a good couple of hours of heating time in the morning, and on the weekends we hit it pretty hard. We dialed back ventilation, we dialed back heating. So a pretty good savings there. And mind you, this is a classroom and office building. When we're talking about laboratory buildings, the savings are probably 10 times as great. We're doing once through ventilation. We're ventilating most lab spaces at 6 air changes per hour, so changing over the volume of air every 10 minutes and heating it and cooling it. This is a little bit more kind of on the administrative side, but we're starting to work with departments now to sort of determine what acceptable nighttime heating setbacks are. So we're working with the chemistry department now in PSB North in chemistry, and they're giving us 10 degrees all night long. Used to be we'd heat all of those lab buildings to 70 or 72 all night and all weekend. And why would we do that? There are some spaces where there are temperature-sensitive instrumentation or experimentation going on, and we don't touch those. But in sort of general chemistry lab type spaces, and most of our labs, we can probably cut a few degrees off of our nighttime heating, and that saves tremendously. If you can save a few degrees on a night like tonight across the whole campus in lab spaces, that really, really adds up.
Second question.
Sure.
Your counterparts at other UCs and CSUs, are they investigating battery storage similarly, and have any of the campuses actually implemented a project yet?
Yeah, so the first campus, first UC campus to put in a battery storage system was UC San Diego. About 3 years ago, they put in a 2.5 megawatt system, and that I think has been a challenge for them. They've also got cogen on campus, and they are not on a sort of classic time of use rate like we are. So some of these numbers obviously paint sort of the best case scenario in terms of savings and payback, and I think San Diego's project has fallen significantly short of what that is. UC Irvine has also put in a couple megawatts of battery storage. Both of those campuses do have sort of advanced fuel research and advanced energy research departments that do deployments like that, and they've gone out and most of that stuff is grant funded. So very similar to what we were trying to do with the CEC grant. And hopefully we won't be too long after, and we'll learn from their mistakes.
Other questions? Yeah.
Maybe I missed this, but there's no wind opportunity?
Great question. That's come up in the past. When I was a student at the Bren School, somebody donated a 10 kilowatt vertical axis wind turbine and wanted to put it in right there next to Bren Hall between Bren and MSI. And not only are our wind resources not really that great here on campus, but our planning department shut it down pretty quickly. Coastal Commission concerns, not only visual impact, but habitat impact and things like that. So unfortunately on campus, that's probably not going to be something that we're able to move forward on in the near future. But there certainly are opportunities on and around some of our natural reserves. I think up at Sedgwick could be a better opportunity than here. Potentially some other UC-owned land that may not be in the natural reserve system. So it could happen.
So Southern California Edison was testing replacing a natural gas peaker plant with solar and batteries. How's that going? Do you know?
Yeah. So conceptually, that's the objective for the replacement of the Elwood plant. I'm not aware of that actually having been built and in practice.
They built it somewhere. It was in Los Angeles.
Down
I
south?
saw figures they showed, but it was probably a year ago.
Okay. Yeah, I haven't seen any data on that.
Okay. Any other questions? All right. Thanks, Jordan.
Thank you.